Well, welcome, coffee lovers. Coffee with coffee lovers, anyway. So thanks for tuning in today. The presenter today is going to be my son, Max Rohr. So I'm proud to introduce him as the presenter for this session. And we're going to talk about hydronic separation. I'd like to think that Caleffi kind of pioneered that in the U.S. market. You know, we had some products available just as the ModCon boilers were being introduced, and it was a good fit for that. So I think we were kind of the leaders in bringing the product and the concept to the U.S. So we've evolved our product. We'll show you some of the things that we've changed and what we're doing with the hydraulic separation. So any questions as we go along, just shout them out, put them in the box there, and we're monitoring questions. If we don't get to you during the presentation, we'll certainly get back to you at the end of it. And this will be available that you can view it on our YouTube channel also. So let me see if we got some more housekeeping here, Max, or do you want to do them? Yeah, so there, if you have an issue with the webinars not showing up or something's going wrong with it, sometimes if you just log out and log back in, you get a different connection. It works fine. But there is a go-to webinar helpline that you can call too if this is a chronic issue with you. But yeah, this will be on our YouTube channel. Typically in about a week, we get it up there, and then you can view it again. Or if somebody in your office didn't get a chance to tune in today and wants to see it, it'll be up there with a bunch of other ones too. And at the end, if you click yes, you can do a post-webinar survey. And if you want a copy of this presentation, you have to do that at the end, do the survey, and then we'll make the slides available to you. And also a certificate of attendance. If we see that you stayed on for the whole show there, we'll send you one of these little certificates with your name on it. It might be good for credits for your license or something like that. We can't guarantee that. It just depends on your authority to have in jurisdiction what they accept for certification credits, recertification. Yeah, if you haven't signed up for coffee or for hydronics, we've got them available now still as a hard copy. We're going to keep that going. They're available as a virtual book, and also you can download the PDF. So I just keep them all on my cloud. So if I'm out on a job site or something like that, I can just pull up a wiring or piping schematic or information. So sign up for those if you do want them mailed to you. We can still do that also. 34 being the current one. Okay, what else here? Yeah, I'll let Max take over on this. He knows a little bit more about the scholarship. So I'll be in the background if you have any questions. Thanks, everybody.
I was on mute the whole time, wasn't I? Okay, so the Alfred Steele scholarship is open right now. If you know somebody in your family, ASPE members or ASPE family members who would be a good fit for that, that is open and will close on January 31st. I just put all that as information in the chat as hyperlinks as well. Okay, next month we have Nicole Harvey. So she's going to talk about some case studies in military bases. So heat pumps, ground source heat pumps in these military applications. That's going to be kind of a cool topic to see when there's lots of policy and lots of eyes and lots of analytics on these different systems to make sure that they work as advertised. And she'll report back with some case studies from those base applications that she's worked with. And then this is me for this week. For this month's Coffee with Caleffi. And what we're going to do today, as mentioned, is go into some of the basics of separation. So this is, sometimes we have more intermediate or advanced classes. This is going to be kind of a back to basics class where we're going to talk about how and why you would utilize different types of separation technology. And if you have been around the industry for a really long time and have another way to describe something and want to type that into the chat, we're happy to read those. We want to make this as interactive as possible because it definitely takes an army of people to describe how to use these different systems, so it kind of works for new people that are coming into the industry with a bunch of different learning styles and ways to pick up the tips and tricks that make the science of our industry relatable. So that's kind of what we're up to today, and I'll get started with the topic. So here's what we're going to talk about. what is primary, secondary, how do you apply it, what is high performance in this case, and then what happens if it doesn't go well. That's kind of the template that we're going to use today. So why do you need hydraulic separation? So we published the first hydronics journal in 2007, and it was on separation. So this has been around, as my dad said, for a long time, really since ModCon started to appear in more projects in North America. This became a bigger issue because what happened in a lot of cases, the reason that we've got kind of the self-explanatory X here, is that in the past, maybe this whole box was a cast iron boiler. And it was pretty flexible to the different flow rates going through that heat exchanger. It was a big buffer capacity of a bunch of cast iron sections that you had a lot of volume in that heat exchanger. So you could have really high flow rates or really low flow rates, and it wasn't going to cause the boiler to run into an overshoot situation or go out on some sort of high temperature limit. Then we came back with these ModCon boilers, which are great for a million different reasons, but have a very much smaller capacity of water inside of them. So they aren't as flexible to high flow rates and low flow rates. If the flow rate's too low and you start to overheat, they have lots of safeties built in that are going to say, hold on, we need to wait a second. We're going to get too hot too fast and shut off. So this scenario where we had maybe 1, 2, 3 of these circulators turn off and we just had one circulator going through a microzone was something that you were going to see 900,000 cycles in a year out of a ModCon in some of the mechanical rooms that I've been to over the years, which is very bad for everything. You're going to run through fan motors and gas valves and things like that because it's just really not what they're meant to do. So that's why this hydraulic separation came up, that like, hey, wait a second, we now have a piece of equipment that really wants a specific flow rate, and we kind of need to change our piping to adapt to that. There are plenty of these systems out there where the ModCon came out. Maybe you're lucky enough to have a couple unions in between, and maybe this is just soldered straight through to kind of do the easiest copy and paste with a new boiler technology, but you're not really setting up any of the equipment for success there. We'll go through some examples why in the next few slides here. But what I'd like to see first, I'm going to launch a poll here. I want to see what type of primary, secondary do you use most often. So I'm going to launch that. If you know, go ahead and select here. If you're looking all the way down at answer E, that is a completely appropriate answer because we advertise this as a basics class. So we are going to go through the difference between all of these. I'm just interested to see kind of right at the top before I go into any of the explanations what the share of the responses is here. I have an idea in my head and it seems to change every time we ask this question, but let's see what we've got. It looks like the results are starting to taper off a little bit here. So I'm going to share those. So we ended up with 20% buffer tanks, 39% closely spaced T's, 24% hydro separators, 2% none of the above, and 15% you're supposed to tell me, which is completely fine. So we'll go on and go through those first three. All three of those are perfectly acceptable ways to do primary, secondary piping. We'll kind of do the pros and cons as we go through. Okay, so here's what I'd like to start with to kind of describe what primary, secondary is. Let's say I came into your office today, whatever your role in the industry is, and said, I created a fantastic machine. I think that we should build this and we should patent it and sell it all over the world. And it looks like this. If this is coming through a little bit choppy based on your internet speed, I'll describe it as well. So the right wheel spinning really fast, the left gear is spinning really slow, and these teeth are in contact with each other. So does this look like a good machine? Does this look like something that you would want to put your name on and put a 10-year warranty on? Probably not. You're either going to bind up, if this were in your transmission in a truck or something like this, this would bind up, or you would strip a gear if there was enough torque to do that. This is not a great machine. This isn't something that is going to last for a long time. We have two different things spinning at different speeds that are in contact. So it is a different analogy. It's different science at play here. We're going to go from rotations per minute to gallons per minute, but it's still just kind of spinning around in a closed loop system. Now, if we use that same analogy here, let's say we've got 5 circulators on here that are going through distribution to this building, but we just have exactly what we need going through that boiler heat exchanger. These two are in conflict here. So if this is just straight through piping, we have two different flow conditions required on the right side and on the left side. And if they're in conflict, somebody loses here. We're either going to have too much flow through the boiler, too little flow through the boiler in some scenarios. That won't work. So the gears in conflict here is one way to think of a system that has two customers that we're trying to address at the same time. This customer needs X number of GPM. This customer needs Y number of GPM, or if it's a variable speed or multi-zone system, this could be any number of gallons per minute. If this is a variable speed pump, it could be 1 GPM, it could be 100 GPM, depending on the system. So we don't want that going through our ModCon boiler or through a heat pump or something like that. We want to make sure that the left side of this equation is getting exactly the flow rate that it needs, and that's why we're going to split this with primary secondary. So the simplest way for me, at least, to think of primary secondary is we just are separating the wheels. We just are moving the gears away from each other so they're not in conflict anymore. So this could be 1,000 GPM, this could be 4 GPM, and they don't fight each other. That's what primary secondary needs to do. And I'll show you the different ways that you can implement that with a lot of different ways to pipe a building. No mechanical room is the same. So that's essentially what we're doing with primary secondary piping. We just want these two wheels not to fight. This one can spin fast, this one can spin slow, and that's great. Inside of a hydro separator, there's not a lot of complexity there. I'll go through some of the things that makes a hydro separator a premium version of this technology a little bit later in the slides, but it's a big open tank in here. So this is allowing that water to be able to bypass back without really interacting with, in a flow sense, the gears on the left and the right. One thing to mention here, and this comes up quite a bit, especially in a basics scenario here, that this is pretty subtle, but you can see this is a darker red and this is kind of a pink, a little bit lighter shade of red. There is some temperature mixing that happens inside of a hydro separator, and I'll show you some of the scenarios, the flow scenarios, in a couple of slides here. They are not, hydro separators, their superpower is not ensuring a specific temperature. So if you need 140 degrees to go out to your system, it doesn't give you a specific number that you need on the input to ensure that. That's all going to be related to the flow rates, the delta T coming back from the system. If you lose 40 degrees of temperature Fahrenheit coming back and you're mixing with something that's 5 degrees warmer on that side, this is not a temperature mixing device. You're going to need some sort of mixing strategy, if that's a thermostatic mixing valve for low temperature radiant or some sort of injection pump, whatever the case may be. This is not a mixing device. It is just something that's separating the flow rates. So it fixes the GPM problem. It doesn't fix the temperature problem. If that's something that you're looking to solve, you'd need to use another component in the system to address low temperature protection for radiant or something like that. So what are the flow scenarios inside of a hydro separator? Let's say, for argument's sake, that we have a hydro separator, and on one side from the boiler here, we have a circulator running at exactly 10 GPM. And going out to the system, very improbable, but let's say we've got the system side is exactly 10 GPM as well. Both of these wheels are spinning at exactly the same speed. So if you put a drop of food coloring right in the center of this hydro separator, right here, if you put some blue food coloring right here and you made this, you 3D printed this entire thing out of a clear polymer or something like that, that food coloring is just going to kind of float right in the middle. There's no cross from the top to the bottom here. It's just kind of going straight from the left to the right and from the right to the left on the way back. So that way, we don't really have much interaction in the center of the vessel. This is the 0.0001% of the cases in a modern hydronic system that you'd have exactly the same GPM, same head loss, same flow rate on both sides. The other 99.9 whatever math I just stated there, sets of times, you're going to have something more like this, where you have a higher flow rate either on the left side or the right side. So we'll say this is a boiler that started up, we're moving 10 GPM on the left side, but we only have one microzone open on the right side. So this is spinning and we just have a little bit of water that's going out to the system. So in that case, most of the GPM. It's just bypassing right back to the boiler. So the boiler is always happy with 10 GPM, even though we have a restriction that we're only sending 2 GPM out to the out of the mechanical room into the distribution for the rest of the building. So the third example is the opposite of that. So we've got the boiler spinning at 10 GPM again, we'll say here, and now let's say we have fan coils or something that has a smaller delta T from the supply to the return out to the system. In that case, we may be moving the same amount of BTUs across here, but this needs to move faster. We're going to have a smaller delta T here. It could be very different if you had a 40-degree delta T across some sort of radiant installation versus a 3-degree delta T for another application. If you're doing something like radiant cooling, you might have a really, really small delta T. And in that case, this is going to be moving a lot faster than the one on the left, even if the number of BTUs exchanged is similar. So what are the 3 different ways that we can do that? So I mentioned closely spaced T's. That was the winner of our poll. Even though from experience that is starting to narrow, I would say if we asked that same question 10 years ago, we would see that closely spaced T's is the vast majority of the systems on the market. The gap is narrowing, and I'll kind of show you a couple of examples of why I think that might be the case. But all 3 are absolutely acceptable ways to do primary, secondary piping. So this is the one that is in the most mechanical rooms in North America. And what we've done here is we've taken that piping diagram I showed at the beginning. Instead of just having all 4 or all 5 of these pumps go right through the ModCon, we've separated them. So we have this wheel is spinning with this boiler circulator. Maybe it's a fixed speed, maybe it's a variable speed, but it's exactly what the boiler is asking for on the left side of the equation. And then these 5 pumps can come and go as they please as the zones open and close, and it doesn't affect the flow rate on the left side. And one of these things that I'll show a couple examples of, or kind of narrate as we go through, that would mean if you took a balancing valve, a flow meter a balancing valve that you could pull a pin like our quick setter and see what the flow rate is, if all 5 of these pumps are running and it's truly primary, secondary piping, closely spaced T's installed, as I'll describe on the next couple slides, you would see 0 GPM going through the boiler. That's how it should work. That's how it should work with all of these different scenarios, and that's how you can test it. So if you turned on these 5 pumps, this pump was off, but for some reason you have 4 GPM going through that, you missed something. There's something sizing-wise, piping-wise that's not right there. You're influencing flow to the left side of the equation. We don't want that. We want these to be truly separated so they can operate independently, and we move those gears out of conflict. So what we're looking for is a specific velocity to make that happen. If we make these T's too small, as an example, that could affect it. If we have 18 inches of pipe in between here, that can affect it. And I'll show some examples of that on the next couple slides here too. Did you have
go back?
Yeah.
Go back one slide. So when I talk to people, especially people on the phone, and they're describing the problem they're having with a primary, secondary piping system where no temperature, no flow, no heat, whatever it might be. In this drawing right here, which side of that is the primary and which side is the secondary circuit? Because if you're not on the same page when you're trying to explain this to somebody, I could be talking about the boiler side doesn't have any flow, and I would say, well, look at that pump. And he's thinking, well, I'm talking about the distribution piping. So here's the right way to know that and to do that and to explain it. Whichever side has the expansion tank connected into it is the primary loop. So if for whatever reason we had that expansion tank connected over on the blue line on the boiler, which would be fine on the suction side of the boiler, then the boiler is the primary loop. In this picture right here, if I was talking to somebody and explained, I said, well, your distribution side is the primary loop because that's the point of no pressure change connection in the system. And that goes way back to the B&G Gil Carlson days. He's the one who said, well, if we're going to do primary, secondary, we need to explain which is the primary loop. And that was the explanation, which makes sense. I mean, wherever you put the tank is the point of no pressure change. That would be the primary loop, regardless if the boiler's in it or not. So just going forward, when you're talking to somebody about primary, secondary, maybe that's the first question you'd ask. Well, where's your expansion tank in the system? And then, well, we're calling that the primary loop. So we're both talking about the same thing.
Yep, and that's a good point. And sometimes to avoid confusion, like you said, you can say, are we talking about the boiler loop here? Or are we talking about the distribution loop? if there is confusion about, like, are you talking about the left or the right here when you say primary? That is the kind of the book answer for which one, but also if that helps for whatever conversation you're having, use the, are we talking about the boiler or heat pump loop? Or are we talking about what's going out of the mechanical room? Just to clarify that, so you're not troubleshooting the left versus the right and running into an issue there over the phone or something like that. Okay, closely spaced tees. That means what to people? How close, how far are we talking? I've seen a lot of boiler books over the years, going back 10 years to some of the installation instructions, and you would see stuff like maximum of 12 inches between, we'll say this is the boiler over here to the left, between the supply and the return. Maximum distance right here of 12 inches. Maybe if you've got 3-inch pipe. If you've got 1-inch pipe, that's no longer acceptable. You're going to be beyond that book answer of maximum 4 pipe diameters apart. So another thing that comes up here, 4 pipe diameters apart is the number that we want to use on center from the boiler supply to the boiler return. If it's 2 pipe diameters apart, that's great. If it's 4 pipe diameters apart, but there's a ball valve in here or something like that, you need to look at the equivalent distance there. So even a full port ball valve, which is just a marketing term, even if it has the exact same inside diameter as the pipe, if this is 1-inch pipe and it's a 1-inch full port ball valve, there is still turbulence there. There is still some restriction, and you're going to have an equivalent foot length penalty there. So in that case, if there were a ball valve right here, it may actually essentially be 8 pipe diameters apart or something like that. So for purging a boiler, it's great to have a ball valve right here. If you put a ball valve right there, then you fill the system, you force flow through the boiler heat exchanger out through the system, and you can do the whole thing in one pass. That's helpful for that task, but it may not be primary, secondary piping anymore. And again, the test is if you put a flow meter right here or on either side of this, and you turn off the boiler circulator and you still see that you have 215 GPM of flow there, that you missed something there and you've induced some flow from the primary to the secondary or vice versa. Another thing that can be tricky about closely spaced tees is you do want some minimum pipe diameters upstream and downstream. So, and this isn't to scale, but you want a little bit of calmness in the piping upstream and downstream. If you just have a 90 right here and a 90 right there, you have a little too much chaos in the center of those closely spaced tees to really let that work to keep those two wheels out of conflict. So that is a limitation in piping that can come up as far as just the space that we have in mechanical rooms, depending on the pipe size that you're working with. So one of the things that I've got a question for the group, you can put this into the chat. We don't have a poll here, but if you want to put something into the chat for what is the key feature you look for to decide. Anybody who answered that poll, if there's a reason that you chose whatever you listed there, go ahead and drop that into the chat, and I'll read through a couple of the comments here. So one of the comments is always instruct people to use the closely spaced tees as close together as possible, and that's always a great recommendation. So we'll keep an eye on that as those chat questions come in. And here's what I wanted to mention next as it relates to closely spaced tees. I'll show kind of a sizing and spacing example in a second. One of the things that we look at when we look at a project, sometimes we'll see that the answer to the last question is what's the key feature that you look for. And every time that this comes up, and we've got at least one of these answers in the chat now, pricing comes up. So if you go to the distributor today and you get a price for 2 1-inch tees and then an air separator and a dirt separator, that will probably every single time be less expensive than a hydro separator if you look at the purchase price. And that's what I wanted to kind of cover here, that there's no perfect answer for this, but know that if you're going to do air separator, dirt separator, and closely spaced tees, if this is press or sweat or hemp or whatever your connection system is, that you're going to have 10 connections that you either do on your workbench or you do out in the field, potential for them to leak. Hopefully not. I know that everybody on this call who's listening to this webinar is likely capable of making all these connections without a leak. But you need to look at the labor required to do that to kind of get a true comparison. Because if we're talking about 4 union connections for a hydro separator, where you can't really mess up the dimensions here, this is going to be the right size, and I'll go into more detail for what that actually means a little bit later. There are a lot of different things that can go wrong here, and best intentions I've seen in the mechanical rooms that I've been to over the years, a lot of things can go wrong here. Spacing wise, there can be, pieces omitted, or this is where you start to see 18 inches of space in between your closely spaced tees. But look at the labor rate. That to know the true cost of the install here, it could be wildly more expensive depending on the labor to do 10 field connections than it would be to just buy the pre-assembled hydro separator from the shelf and toss it on the wall with a mounting bracket. So again, I'll do my best to not play favorites here, but that is a consideration. If somebody can do this for $10 an hour, go for it. If your labor is more expensive than that, which I assume that it is, it starts to change the equation a little bit. Okay, here is, not to scale, an example of how big closely spaced tees can get if we're following all of those rules. So if we have the straight pipe lengths upstream, downstream on the system side of the separator, that can start to get a little bit bigger on the wall than it would seem. So closely spaced tees, when you pick up the tees and they fit in your hand, it seems like that whole thing is going to be small, but to follow all the rules, it can turn into a little bit bigger assembly than it seems. And this job is a really great example. It's hard to see without the insulation here. This may be right at the edge of 4 pipe diameters apart here. So this might just be a tiny bit out of tolerance. Maybe not, it's hard to tell, but that's where things start to drift a little bit. So you take up a little bit more space here, and you might just be influencing a little bit of flow from the left side to the right side of the equation here. This system will work fine, I'm sure, but that's where we start to drift out of tolerance a bit. Okay, so let's move on to another way to do primary secondary. This absolutely will work as well. Buffer tanks became popular with mod cons as well. I'll kind of go through a sizing example. So we didn't use buffer tanks because the cast iron boiler was the buffer. There was a lot of volume there. Then buffer tanks got really popular with mod cons for a minute. And then the mod cons got better at the turn down ratio. So now they're going down to a 10-to-1 turn down or something like that. We don't really need the buffer tank as much. I'll go through the sizing piece. And now with heat pumps, because they can't quite do a 10-to-1 turn down or something that a mod con can do now, buffer tanks are starting to come back a little bit. So buffer tanks have been up and down. I'll show you how you would know if a buffer tank is a good idea and what problems it would solve and how to size that. It absolutely will work as primary secondary piping because it's just a really oversized hydro separator. So if you had 10 GPM here, it's going to go into the boiler. If you have 100 GPM on this side, this vessel is big enough that it can just kind of spin around really fast without fighting with the other side of the equation in our primary secondary piping diagram here. How much buffer tank do you need? I won't go into a ton of detail here. This is in our Hydronic 17. I've got the link to Hydronics in the chat there if you want to go and pull that up and download the 17 version. Here's what we're looking at. We need to know these 4 variables. So let's say that we have a 50,000 BTU boiler and it can turn down at a 5-to-1 turn down ratio. That means that the smallest amount of energy that it can sustain to come out of the mod con is 10,000 BTUs per hour. This is an important one. How long do we want the buffer tank to buffer the ability to, how long do we want the battery to last when we charge it up? 20 minutes is a good place to start. If you put in 5 minutes here, you're not really providing much of a buffer. We want to give that boiler a little bit more time to rest. You could do 1,000 minutes here and have a 500-gallon buffer tank. That would be overkill in a lot of cases, but mostly we just don't want, especially a boiler or a heat pump, to cycle 10 times in an hour. 20 minutes is probably a good place to start. Now, the next important variable is what's the smallest load? What is the micro load in the building? So for argument's sake, we'll say this zone number 5 is a towel rack in a master bathroom of a big custom house or something like that. And we can only get 1,500 BTUs per hour through that towel rack. That is our smallest load. Worst case scenario, maybe that doesn't come up very often, but that's the worst thing that could happen. We want to allow that buffer tank to drop 20 degrees only. If it drops 100 degrees, then you might start to feel cold water in the towel rack or something like that, which we wouldn't want. So we plug all those things in, and in this case, we get a 17-gallon buffer tank. Don't even know where you'd find one of those, but just to kind of illustrate that with a ModCon or something that has even a 2-to-1 turn down ratio or something like that, it really takes the size of the buffer tank down, and you won't need as much as you may assume if you thought that it always had to be 119 gallons or 60 gallons or something like that. That's the formula with the ModCon to figure out, or anything that modulates that you can find the minimum turn down ratio or equivalent with a heat pump. That's how we're going to size a buffer tank. How do we pipe these things? So the typical one that we use in the rest of the slides is as if it were a hydro separator. This can be a good fit in a lot of different cases. One of the things that I mentioned briefly from a temperature perspective that can be an impact to choose a 4-pipe configuration with a buffer tank is that if this is a 140-degree supply and we need 140 degrees for our heat loss for whatever our terminal units are out in the building, we might not have that. We might have 140 here and 135 by the time it mixes with the return based on whatever the flow rates are going out to the building. So if that's the case, a 4-pipe tank configuration does lead to mixing in this vessel. So we're going to shave a couple degrees, maybe only a couple degrees off of the maximum outlet temperature here. We had this come up with a project I was involved with a long time ago where they had 180 degrees coming out of the boilers, but the indirect tank was piped over here. So they had an outdoor reset schedule for the building. So in the summer, they didn't need 180 degree Fahrenheit water to go out to the building. Unfortunately, they always needed 180 degrees to go to the indirect coil that came off here to heat water for the building. So because of that, they always had to have this buffer tank at 185 degrees to make sure that they got 180 degrees through that. And that was a very warm mechanical room because that buffer tank was huge, and you just had an enormous column of water sitting at 180 degrees all the way through the summer. So that made for a toasty mechanical room. The better way to do that would be to pipe the indirect tank off of this side, so we can just have the boiler or the heat pump heat up the indirect tank, and then the buffer tank in the middle of summer does not need to be 180 degrees if the heat loss calculation, the outdoor reset curve says we only need 110 during the summer. No need to heat that whole thing. So that's a limitation of a 4-pipe. You're gonna have some mixing there. So these two examples are a little bit trickier, just as far as the piping goes that you look at here. There's a little bit more complexity. What this allows you to do is send the hottest water from the heat pump directly out to the building. So you can go direct to load here. So this 140 degrees from the heat pump can go right out to a radiator or to the radiant heating or something like that. It doesn't have to interact with the buffer tank. So in this 2-pipe configuration, we could have all the zones come on, 140 degrees comes out, whatever comes back, and we just do that. We basically haven't engaged the buffer tank at all. Until we start to lose some zones here that they start to come up to temperature, and then the heat pump, some of those GPM start to curl off and heat up this tank. So we start to charge the battery. Then the heat pump turns off. If this is up to 140 degrees and one more zone comes back on here, we can actually pull flow from the right to the left to go out and heat up the building there. So water can be going both directions through this span of pipe right here. This is a system that I know that my dad had running in the shop that he had in Missouri for a long time. So this will work. This goes direct load, which is an advantage. This 3-pipe is similar, but on the way back, the water is coming back through the bottom of the buffer tank. So you're always charging that buffer tank on the way back. So if you turn on this heat pump, it's not going to turn off until you get your tank sensor up to whatever you wanted to there, if that's the way that you set it up. So you're always going to ensure that you charge the buffer tank at the end of the cycle. Is that a good explanation for what you had in the shop in Missouri there?
Yeah, I mean, that pretty much explains it. It's called direct to load piping. So if there's no, if both the load and the boiler is putting out the same GPM, nothing goes through the tank. So that's the nice thing about it. And then when all the zones go away, the tank charges up. You charge the battery, and I don't know if you can. I'll turn on my camera here, see it, but I just put a a buffer tank. I just put a heat pump, a Viessmann heat pump in my shop, and you can see the two pipes come off the side there. So my heat pump module right there ties into the buffer tank, and my boiler ties into the buffer tank too, and then my loads come off of the buffer tank. So any one of them, or they could be working together. The heat pump could, I'm not keeping up, kick on the boiler, they could work together, they could work independently, or I can be pulling off the hot or chilled water off that buffer tank without either of the inputs, which I'll call the boiler and the heat pump running. So this one is pretty nice. The three pipe, did you talk about that one a little bit? Takes it
Yeah.
one step further. And what it does is on this three pipe, all the return water comes straight across the tank back to the heat pump. So you're going to get your lowest possible return temperature. This could be a boiler, could be a ModCon boiler or a heat pump we're showing in this, which will keep the efficiency of that device up. The cooler the water comes back to it. With this one here, you don't get direct back to the through the tank. So we're still engaging the tank up here on the top, but by coming through the bottom straight back, we're going to get the lowest supply. So they all have pros and cons. I mean, obviously it's a little bit more piping involved, but what happens on both of these here, this is a hydraulic separator right here. So this piece of pipe has to be big enough if we had multiple, which I do on mine, multiple pumps connected right here. This has to be a piece of, well, in my case, 1.25 inch, 1.5 pipe, so that these pumps can run like this, pulling right off of here without affecting flow through the tank. So there are some fine points. If you're going to do a 2 or 3 pipe buffer, you got to make sure that you have a generously sized, we say generously sized. Basically, we want the flow through this pipe no more than 2 feet per second when everything's running. So that pipe, you have to add up the GPM of all your loads and then look at a piping chart and say, okay, I've got 18 gallons a minute. I need 1.5 inch copper pipe or 1.5 inch steel pipe to assure I get my separation here. So
yeah, the very technical term being short and fat there. That's what we're looking for that little span. Okay, so here we used to sell these when we were doing more solar thermal systems. So again, this may be properly sized for what we were doing there. In the case in my dad's shop right there, that was a much shorter version of a buffer tank for the application that he's got there, and that works great, and they fit in the mechanical room better. So here is the third of 3 primary secondary examples with a hydro separator. We talked about this a little bit before. Here is kind of the golden ratio here. We want the barrel of the hydro separator to be 3 times at least. If it's 5 times, it's a buffer tank. Anything bigger than that 3-to-1 ratio, you're just kind of moving into buffer tank territory. We want it to be 3 times the inlet piping, properly sized. So if this is 1-inch pipe coming in here, the barrel of that hydro separator needs to be 3 inches for this science to work, for the wheels to be out of conflict. If you make that you can absolutely make this less expensive if that's 1.25 inch barrel from the top to the bottom. You may have broken that rule of primary secondary piping, and again, you will absolutely be able to test that if you put in a flow meter right here and see if there is flow induced from left to right when you get to the maximum flow rate that was advertised for that hydro separator. If it says that it can take 40 GPM and you turn on 40 GPM worth of system flow, and then you see past 35 GPM that this has 1, then 2, then 3 GPM of flow rate on the left side here, we just aren't separated anymore. So one of the reasons that works well for a couple other things that we'll talk about, this 3-to-1 ratio, is you're going to have a 1/9 velocity inside of that chamber. So it really calms down the flow, and that helps for the air and dirt separation as well, which I'll get into towards the end. So this is the smallest version of a buffer tank that will still work for primary secondary piping, is kind of what we're doing here. So here's another example I'll go through. This was the look on a bunch of faces when I did a presentation like this at a trade school that was a 6 to 9 p.m. class on a Thursday. So a lot of these techs had been at work all day, and then they came and had the pleasure of me talking to them as they were like ready to go home and clock out for the day. So I could see that the eyes were starting to droop a little bit. And I said, okay, we're going to talk about primary, secondary piping. Everybody get out of your chairs. We're going to set up 2 different tables in this big training room. So we had a table over here and a table over here. I put 5 people on one table, 5 people on the other table. And I said, just start walking around and see if you can walk around at exactly the same pace. So I changed these to yellow and blue just so we can kind of see in a second how that affects it. So We've got both of them, both tables started off at about the same rate, so everybody's moving along pretty well. They're starting to wake up a little bit. Now, I'm going to move these tables closer together. So as they were doing it, as there was a gap, I started to push this table on the right a little bit closer together. So now we ended up in a situation where this was primary, secondary, completely separate circuits here. They could walk around at a fast pace or a slow pace, and they weren't running into each other. Now, even though they were going the exact same speed or as close to it as they could, we have a little bit of a pile up here. So we have some traffic. We have to wait until this person is out of the way because we don't have enough space anymore here. So we've started to break that 3-to-1 ratio a little bit. We can't get flow on the right side and on the left side going at independent speeds. They're now affected by the amount of traffic on the other side. So now we keep going after these people waited for the logjam. These people are still on pace. This side, they've slowed down a little bit. Now we've got an even bigger collision. So I move these tables closer again, so they almost have to turn sideways to get past each other. Now we've got a problem. Somebody has to stop here. So either this yellow person has to stop or this person has to stop and they have to squeeze through. We have some traffic here. So what I did is I had everybody stop. Say, okay, everybody stop moving. Now, this person right here, would it be easier for you to keep up the pace if you waited for this set of people to come all the way around, or if you just went into the other circuit? So it is easier for that person to just jump to the other side. So in that case, this person, instead of going and fighting through everybody to go between the tables, said, you know what, it would be much easier for me if I could just go to the other side here. And they started joining this other circuit. Now we don't have the balance that we thought. We have people joining the wrong circuit, and that's kind of influencing the flow at this decision point, as if you were a molecule of water or glycol or whatever, that you have to decide, is it easier to go left or right here? And that's kind of what happens when primary, secondary rules are broken. We now have more flow, more people in this analogy on the right side than we do on the left side, and that's are breaking our rules with primary, secondary piping by not having that golden 3-to-1 ratio anymore because we squeezed it closer together. Okay, so now inside of a hydro separator, there are a lot of different ways to build these devices. So we can have a very simple hydro separator that maybe is just a completely open vessel or has a baffle or something like that. I would call this kind of the minimum device to do primary, secondary piping. This is going to be more cost competitive without some of the high performance features I'll talk about on the right side here. Absolutely will work for primary, secondary piping. Is it high performance air and dirt separation? Not really, and I'll talk about that more as we get closer to the end of the presentation. So this will still work as a primary, secondary device, but when you get to a high performance device, the way that I would describe that in generic terms, we have to have some sort of collision media inside there, and different manufacturers do this with different materials. We have to have something in there that helps facilitate the separation of air and dirt. So some sort of coalescing media that I'll go into more detail with when I get to that section. That's what I would describe the difference between standard and high performance there. So again, if this is the 3-to-1 ratio, both will absolutely work for primary, secondary piping, but it's going to take you longer to get air out of this system, and you may have some dirt go right through and get back into a heat exchanger somewhere else if you are using a standard versus a high performance. So not all interiors of these devices are decorated the same, I guess, and that's what kind of moves to a premium capacity separator. And this one also has magnetic separation, which I'll get into more as well. So this was a pre-submitted question. How do you size these things? So let's say we know on the primary side, which we'll say it's the boiler side and it has the expansion tank there. So that's our primary. We're moving 140 GPM through the boiler. We've got a different delta T design for the secondary side that's 230 GPM. We just take the bigger number, and that's what we want to accommodate with our maximum size for our chart. Whoever's making the hydro separator, that's what we're looking for there. So we need 247 here. That's going to cover our 230. We don't need 370 GPM. We don't need to move to a 6-inch separator. You'll absolutely make the wholesaler and the rep in your territory happy if you buy a 6-inch instead of a 4-inch in this case. And it's just a buffer tank. It'll work great. but it's overkill. It's more than you need. So just pick the bigger number, either the primary or the secondary, and select based off of that. This was mentioned before. I won't spend a ton of time on this. This is an Hydronics 15 if you want more detail here. The expansion tank can be in a few different spots with the hydro separator. We can do it right before the inlet of the pump, right here. That's always a great spot in any scenario to put your expansion tank right before the inlet of the pump, so you're pumping away, like Dan Holohan has said. In a hydro separator scenario, since the pressure drop is so minimal, almost negligible right here, you could actually put the expansion tank right on the right side of this hydro separator and it would work okay. One place we don't want the expansion tank is right below it, because all this dirt is going to collect here and then it's going to fall down onto the diaphragm or the bladder of the expansion tank. We don't want a bunch of dirt sitting there. Also, as the temperature of the system changes and the expansion tank works as it should and it expands and contracts, it could just inject all that dirt right back into the boiler, which we don't want. So we don't want the expansion tank right there, kind of having flow up and down through this vessel from the bottom isn't good. That's where our dirt collects. We want to do it to the left or the right in this scenario, but either would be acceptable.
One of the typed in questions asks why we pump into the boiler. So go back on that slide and I'll show you a little example here. So that boiler in the picture right there is what's called a water tube boiler. And this is what it looks like right here. This is one of the sections that came out of that exact boiler. And if you can see the passageway in that, I don't know if you can see it in the camera very well, we hold it against the white, it's pretty small. So why we pump at that boiler is because the pressure differential that circulator adds to the system when it fires up goes into the boiler to overcome the pressure drop of that coil. So we want to use our pump delta P pressure differential that anytime a circulator starts up, it increases the pressure on the outlet side. If you had a pressure gauge right there and you plug that pump in, you would see it would go from maybe 12 pounds fill pressure up to 18, 20 pounds, depends on the side of the pump. We want that to go in through that tight heat exchanger, so we're sure that we get flow and we scrub that heat exchanger, keep it clean, scrub the heat out of it so it doesn't overheat. If this was a cast iron boiler, yeah, you could have that pump on either side, very low pressure drop, and maybe a steel or a cast iron electric boiler, the pump could be over here. But if you do have one of these fire tube, not a water tube, but a fire tube, or a water tube, not a fire tube, sorry, a tight boiler, let me say, a boiler with a high flow resistance, which it'll tell you in the installation manual. It'll usually tell you what size this pump needs to be, and that's another way that you know, oh, I've got a pretty high pressure drop if I need a 2699 pump to just pump through my boiler. So that maybe answers the question best.
Yep, and that for a heat pump as well, that's going to be a higher pressure drop across that heat exchanger, so they're probably going to tell you to do the same thing to pump into it. So here's a good example. If we did this, I can't quite tell what the pipe size is here, but we'll say it's 2-inch copper. If we did this with closely spaced tees, that could be wider than the shoulders of the two guys who are so proud of their work here. This is a great looking project. Absolutely could do it with a buffer tank or closely spaced tees. This is a pretty small envelope to be able to do this, and that's an advantage to the hydro separator. You can also pipe right into this with 90, so we don't have that straight distance of pipe to the left or right like we did with the closely spaced tees. So if we were going to do this and add closely spaced tees, we would have to take a lot more real estate in this mechanical room. This is a very luxurious size for a mechanical room. When I worked in Colorado as a manufacturer's rep, this is bigger than 99% of the mechanical rooms that I was in, even if they were moving more BTUs and had more boilers in and out of that space. So this really made that task a lot more compact. And also we just have 4 flanges to connect to keep 1, 2, 3, 4, 5, 6, 7 circulators kind of operating independently, which is exactly what we want there. So this is a great example of that, just as far as the space goes, and the implied labor savings of not having to do 10 soldered 2-inch copper connections in that mechanical room as well. This is a chilled water scenario. So you can absolutely use these hydro separators for chilled water. You just have to insulate it really well, as you would for anything else. What changes is you actually kind of flip the piping upside down. So the hot water is always on the top, which in a chiller scenario would be the return instead of the supply. Okay, got another question in the chat here. what is the primary reason you do or don't use a hydro separator? I'm kind of interested to hear just in general what the decision point is, and I'll kind of keep an eye on the chat as I move through here. But put anything that you love or hate about the device that you use most often. And then for the last part here, I'm going to switch over to air, dirt, and magnetic separation, and we'll move through these kind of quick. We wanted to focus on the hydro separator, primary, secondary portion for the majority of the class here, but I'll go through what's going on inside to make the air and dirt work well. So an air vent is something that's going to get air out of a system at the high point. It isn't going to send the air to the high point. That's what an air separator does. An air vent is just something that's going to let the air out if it has accumulated at the top of something. That's why you'd see an air vent on a riser, solar panel, top of a separator, top of this manifold right here. That's where the air is going to go just because it's more buoyant than the fluid that it's in, the water and glycol mixture or whatever. We had a pre-submitted question, why don't you see potable water air separators? So there is a potable water air vent that we have in our catalog. This is called the plumb vent, and it is low lead. So if you did want to put one at the top of a plumbing riser that it was having air issues or something like that, this one is capable of doing that. But most of the time, since these are all hydronic examples, you're going to see more air vents in a hydronic system than you would in a plumbing system, but it is an option. So what's going on inside of an air vent? Got a very simple manual air vent that you can open it up and let air come out of it if this is in the side of a radiator or something like that. And then you can twist this to an automatic mode where it's going to let air out unless water starts to come out. And then these little fiber gaskets are going to swell up and they're going to seal. So if water starts to come out, it's going to seal. Very, very simple technology for a manual air vent. An automatic air vent may still have those little fiber washers. This is an accessory that works with our air vents as well as other competitors most of the time, because it seems to be a similar thread on the top that should be the same across a lot of different brands. So an air vent, an automatic air vent, is a little bit different because when air comes up to the top here, it's going to allow that float to drop. This is just a little needle valve, like a Schrader valve in a tire or something like that. So as the float drops, the air is going to vent out. As the air is vented out and the float comes back up, then it closes up the needle valve. One thing to pay attention to here, you want this little pocket of air here. What I have done before is taken a little like control screwdriver and I push down that needle vent until all the air comes out and I get a little splash of water out the top and I think, okay, that's great. We got all the air out. I actually don't want to do that because if I do that, this little air pocket here is actually a good buffer to keep the Teflon tape and a wood chip or whatever may float up to the top here, little pieces of plastic or something like that, from coming in contact with an air vent. So if you've seen an air vent that's dripping in your career, there's something hanging up that little needle valve right there, and we want to keep the potential for collision with that from other debris in the system minimized, and that's why we keep that little air pocket there. So once an air vent, an automatic air vent has stopped venting air, just leave it. There's still a little bit of air in there. It may be a quarter of an inch, it may be 2 inches, depending on the size of the vessel, but we want that to stay separate from the water level at the top and the needle valve so it has the longest service life. So what's the difference with an air vent and an air separator? It's the bottom half of this device here. So this is our coalescing media, which is a very fancy way to say to gather. So coalescing is to gather these air bubbles so they don't just blast straight through the device. It's going to catch on these little sharp knife edges of this polymer media that we have here. They're going to build into bigger bubbles and then they're going to go up to the top. So an air separator is grabbing and separating the air out of the system. An air vent really only vents air that's accumulated at the top. So if we just had a T here with an air vent coming out the top, we're going to get a little bit of air. We're not going to get a lot of air out of that system because the velocity is going to take that entrained air, the little micro bubbles, right past that separator and out to the system. So coalescing media is what makes a separator and not just an air vent. Also, just the big bell of an air separator slows down that velocity so it's easier for the air to separate. So you can cut some cost out of these and make them really skinny. They're not going to separate air as efficiently. Okay, so the air we're trying to separate with these devices, big air pockets, like when you first hook up a garden hose in the summer and you have the kind of like water than air, big pockets there, most devices are going to catch those. That's something that like an air scoop like this is going to be great at catching those big pockets of air and sending them up to the air vent. The entrained air, if you filled up a glass of water at your kitchen sink and you see that there are bubbles in there, it looks milky to start, and then it kind of becomes clear as the air bubbles come to atmospheric pressure. Those are the hard ones to get. Those are the ones that'll zip right through a scoop style separator, a scoop style air vent, really. That's what we can catch really well with an air separator, because they're going to hang on those knife edges of the media there, and they're going to gather and become bigger bubbles and float out the top. So one of the things that we had another pre-submitted question here, and this is an analogy that you probably did not see coming today, but a tangential separator. Let me switch over to a different pointer here. I'm going to use a pen. So a tangential separator is used mostly in commercial. I don't know that I've ever seen a residential one. And it's going to have offset inlet and outlet of the air separator. And the idea is that it's going to create kind of a vortex in here, and it's going to spin around, so then the air is able to come out to a vent in the top here. So like ribbon dancing in the Olympics, it's only really worthwhile if it's spinning around a lot. So if you have a really low flow rate here, all those air bubbles are just going to go straight across. So if you see a tangential air separator, it's going to have a very specific flow rate that it likes. It has to be enough to create that vortex to be able to have the air swirl around in this device and come out the top. If it's too low or if it's too high, you don't quite get that same performance out of those devices. So again, they will work. It's just not something that works across the entire range of flow rates, the same way that an air separator, has a good range from 1 GPM to whatever its maximum GPM is. So without that vortex, you're kind of missing something. If you've got a single speed pump and it's always going to be exactly that condition, then a tangential separator sized correctly will work. But if you've got an ECM pump, if you got variable flow, you might have that just crossing straight across an expensive commercial device, and that's not what we're looking for there. So the location of these devices, an air separator, we want it in the hottest, lowest temperature spot. So this is a lot more detailed than I'll go into in this presentation, but the hottest spot on the outlet of the boiler before the circulator is where we're going to have the best, lowest solubility of the air in the water. So it's going to come out of solution and we're able to vent it. If we put that in position B, the pressure just went way up because we boosted it with the circulator. So the temperature is still hot, but we kind of force all those air bubbles to go back into solution, and we can miss them and they'll come back out of solution somewhere else in the system. Here is the performance of these separators. One of the things that we talked about before the webinar started is that the reason that we don't have a potable water air separator, one of the reasons is because they're multi-pass devices. So if we had a low lead 1-inch air separator that you put on the inlet of the water coming into your building, we don't have multiple passes there. We have a single pass. So we're going to get some of the air out, but at a single pass, we haven't removed the percentage of air. We haven't removed a high percentage. It's going to take a few seconds in this graph or a few minutes, depending on the system size, the volume, to get all that air out. It's a multi-pass device. So the way that we size that is 4 feet per second is a good maximum to use for the brass devices. It's also a good number to use for the steel devices. We will publish a higher flow rate, but it's just going to take longer to separate that air out. Over the course of the day, it's probably going to get to the same 99.9% air removed number, but that's one thing to keep an eye on. Also, if you're trying to move 100 GPM through 2-inch pipe, you're probably breaking some other velocity rules somewhere else in the system. So they don't stop working at 4 feet per second. You're just going to stretch out that performance a little bit. With glycol, you're going to stretch it out even further because it's harder to get that air out of the kind of oil viscosity that glycol can have sometimes. So it'll take a longer amount of time to get that performance. Okay, we are at the end of the presentation here, so I'll go through these a little bit quicker. Dirt separation, same concept. We've got a big open vessel here that slows down the fluid coming in, so we're able to separate the dirt better, and they don't plug. So as the dirt separates, it's going to come out of the flow path here, where in a Y strainer, it's just always in the way. So you're always trying to pump past a growing number of things that are blocking your Y strainer. So as a Y strainer becomes 70% plugged, look at how much pressure drop you've added to that system. So in this case, if we're at 14 GPM and it's 70% plugged, we've added 5 PSI to that pressure drop across that device, which is really going to affect the flow rate that you need for the system or for the boiler, if that's the case. You can also just get much smaller debris out with a dirt separator down to the diameter of your hair that would go right through the basket of a Y strainer, but eventually will hit and collide and fall down to the bottom of a dirt separator. Another advantage kind of matched with the technology in the industry is magnetic separation. So a magnetic separator is going to catch the magnetite and it's going to cling to the magnet. The devices that we make are all in a dry well. So you turn off the system, you pull out the magnet, you pull this one off of the outside, the magnetic debris that kind of looks like an Etch-a-Sketch falls down to the bottom and you purge that out. Without the magnet there, it's going to blow through and it's going to find its way to another magnet, which unfortunately might be a really expensive part of your system. The rotor of an ECM circulator is magnetic and it's going to catch all that magnetite if you don't catch it with a stronger magnet upstream. That's kind of what we're doing there to protect that ECM technology, which is going to be the only option that we have very soon, which is great from an energy efficiency standpoint. We just have to protect them well. This is a little bit of both. So this is a device that we make, the XF, that is a dirt separator in the same way that I've described, but also has a Y strainer, essentially a mesh strainer in there. And then you can rotate that gray knob at the top and it uses like a bristle brush to wipe it clean and then you can blow it down. So this is for really, really high performance dirt separation with a magnet in it as well. For like a heat pump is kind of what we developed these for, with really small heat exchanger passages with existing systems. That's what we intended there. So kind of best case scenario for dirt separation and straining really. Okay, here's what I would recommend if you're going to blow down these devices. Do that into a cup or a white bucket if it's a big system, and then take a magnet and see how much of that debris reacts to it. If you've got a lot of stuff that's following around a magnet on the bottom of the bucket, you probably have a leak somewhere. If that's not just the same amount that, if you continue to see the same amount over and over again, there is air in that system that is rusting the system from the inside out. If you still have buckets of magnetite over and over, that may just be the case. If you have old cast iron radiators that will never really seal completely, that may just be something you fight with forever. Otherwise, you might have a leak somewhere that you can't see. You want to turn off that autofill valve and see if you can find that so you're not just bringing fresh oxygen into the system to keep rusting away your components forever. So to wrap up here, air vents and air separators. Air vents for this side here, same functionality, big down to 1/8 to big air separators. And then from 3/4 to 14 inch, it's the same device, just a slow spot in the system with a coalescing mesh to help separate the air. Dirt separators, same thing, 3/4 inch to 14 inch. All these devices are going to look similar on the inside. This has a polymer media. This is stainless steel because we have to weld it together. Otherwise, you'd melt the polymer there. And then in some cases, an air and dirt separator combo can be a good fit. And I saw this as one of the questions in the chat. This is intended for a chiller. So the idea with an air and dirt combo is that the hottest air, like we talked about, the lowest solubility before you get to the pump, before the pressure increases, and the dirtiest fluid is going to both be on the return before the chiller. So that's why we use an air and dirt combo here. But if this were a boiler, the air separator would be good on the hot point of the system, which would be on the outlet. The dirt separator, we want to catch it before it gets to the expensive stuff. So you can, in hydronic systems, use an air and dirt separator combo. It saves some space, saves some money on the job. But really, you have to pick if you want to have it perform best as the air separator or the dirt separator, because it won't be in the same spot necessarily for a hot water hydronic system. And then to wrap up here, since we're at time, I've got a couple just glamour shots of kind of all this coming together. So this is a project near Aspen, Colorado in Snowmass, that lots of different boilers, 2 ECM circulators over here, and they solved some major air issues in this building that were causing lockouts in the fin tube up in the units of this expensive condo building. And all of these pumps are happy. Got 4 different system pumps, got 2 different ECM pumps. They are separated from left to right here with that separator, and that's exactly what we're trying to do on a much more complicated commercial scale. Same thing with multiple boilers here going out to a big building that our rep in Canada and Ontario, this project Equipco put together. Looks great, really small footprint, and we can take 90s right into this where we wouldn't be able to do that with closely spaced tees. So I'll wrap up there. I'm a couple of minutes long, so I apologize for that if you've got to run to another meeting. But why don't we take a look at any other questions that came through and see if there's anything else that we can answer while we're on the call, or if I hear my dad went and got that heat exchanger in the middle of the call. If there's something else you want to take a look at that we can pull up right now, we're happy to do that. And then here's our contact information. If you have anything project specific that you want to ask us about, we're happy to get back to you by phone or by email there. So let's see. We've got a question about the velocity drop caused within the hydro separator. So that 1/9 velocity, because we're going from a 1-inch pipe to a 3-inch pipe, that's where that velocity drops, and that's where it becomes so much easier to separate the air out. So if you imagine a river coming out of the mountains, moving really fast, a lot of turbulence, a lot of air kind of tumbled up in the water, that could be your 1-inch pipe. And then when it gets to the lake at the bottom of the valley, that's where you don't really see water in a lake that's all churned up, unless it's at the bottom of a waterfall or something like that. It's because it's slowed down enough and that velocity has decreased that the air that was kind of tumbling around in the washing machine of the faster flow has the opportunity to come up to the top of the lake. That's what we're trying to create. The air separator is just a little bit of a lake in that system where we can slow down the velocity and let that vent up to the top. Okay, there was a question about the percentage of glycol for performance of air separators. I think we have that somewhere from our testing, and I can follow up with that one after the webinar and see if we can get some performance there.
And just
Won't
know
have a
that
specific number. Yeah, go ahead.
glycol takes a long time to get the air out. I started this little heat pump, and it took all day for and it holds like 6 gallons of fluid because I put a heat exchanger. It took 4 hours for that glycol to go from cloudy to just blue clear fluid. It's just a tough fluid to get air out of. Now, if you can heat it up, get up to 160, 180, it'll come out a lot quicker. Obviously, my heat pump's running at 115, so that was probably part of the reason it was taking a long time to get that air out of glycol. But it's just be patient with glycol. Don't say your hydro separator isn't working right because my glycol still got air in it. It doesn't give up its air very easily, especially at lower temperatures. So.
And we did a glycol webinar earlier this summer. Glycol is great at not freezing. Other than that, it's something that we wrestle with in hydronic systems for air separation and heat transfer and things like that. So we had a really good webinar that's on the YouTube channel about glycol earlier to kind of go through some of the things that glycol is great for, but don't overdo it. We don't need a higher percentage than is required because it's just going to make all that harder, and just expect more time.
And another good question, would putting an auto air vent on the return line suck air into a system? And that's a good question.
That's a good one.
Yeah, and yes, in fact, it can. But if that's happening, you've got a subatmospheric condition in your piping. If you've got a picture, one of them here.
Let's see if I can go back
and usually what causes that to happen, and when you have a job where you got a chronic air problem and every plumber in the city has gone over and bled the system out and they still have air problems, you're probably pulling air in through an auto air vent. And what happens, what causes that, if you've got your pump pumping at the expansion tank instead of away from it, what happens is the differential that circulator is making in the system is on the return side, and you can actually pull a system that you had pre-charged to say 12 psi, your fill valve put at 12 psi, you start up your pump, it's pumping in the expansion tank. If that pump can make a 12, 15 pound differential, you're pulling a negative condition. So if you have an air vent on the suction side or on the return side of that system, you can in fact pull a sip of air in every time that circulator starts up, and then you get the call the system's noisy again, and you go back and you purge it, and it's fine for a couple of days, a couple of weeks, and you got an air problem again. Look at your relationship of your pump to your expansion tank, and that's what you need to make the correction to stop that. And we've got a really good B&G drawing on that. You probably don't have it in the stack of slides that shows that relationship of the pump and how it changes that. And it's in, I think, 3 or 4 of our hydronics we use that Bell and Gossett example, because it is a really good example of how the relationship of the expansion tank to the circulator determines what the pressure is throughout the system. If you put a gauge all throughout your building, you can see the pressure change. based on the pumping relationship.
So yeah, I just kind of drew it with my cartoon drawing here. But if you had your expansion tank right there, you're basically just like pushing into the spring. Then you can go subatmospheric right here, and you'd actually have flow into the air vent, which we don't want, as you just described. We also had a question about, let me go back to the end here, about the top here. So what is this at the top of an air separator? In these big commercial devices, it would take a long time to get all that air out through this 1/8" cap at the top, or smaller than that, through the top of the air vent. So this is a gooseneck that comes up into the device here. You could hook this up to like a water heater hose, take that down to a floor drain, and you're going to allow air to come out at a much higher flow rate until you start to get a little bit of water. Then you close that back up, and then this isn't really needed anymore, and you put back into automatic mode with the air vent at the top. That just kind of speeds up the process a little bit instead of kind of getting an enormous air bubble to come out of that air vent. Might take all day if you were just going through here at the initial startup. So that's where you would use that gooseneck. Okay, let's see. Do you see any other questions that we should snag while we're...
I think a lot of them were answered throughout the presentation. Some of them, obviously came up before you got to the slide, but I'm scrolling through them. I think you answered them, and I'm sure anything that we didn't catch, we'll respond with an email.
Okay. I just got into super speed mode there. Okay, with that, then I'll go back to the end of the... it's going to take me too long at the end. I got it. There we go. So thanks for joining. We'll see you again next month. We're going to do it a little bit early so we miss the holidays, and we'll be talking about some ground source heat pumps in military applications, which will be a pretty cool set of case studies with Nicole Harvey. So thank you again for attending, and we will see you next month. Bye.